As the human body ages, its metabolic systems are increasingly taxed by oxidative stress, inflammation, and declining hormonal regulation. These shifts contribute to the growing risk of chronic diseases such as type 2 diabetes, cardiovascular disease, and cancer. Yet among the oldest old, those who live beyond 95 or even 100 years, there is a striking deviation from these trends. Many long-lived individuals exhibit distinct metabolic profiles that not only resist age-associated deterioration but actively support continued physiological function well into late life. Their blood chemistry reveals subtle but consistent markers of preserved insulin sensitivity, favorable lipid metabolism, and enhanced antioxidant defenses, suggesting that metabolic health is not just a consequence of longevity, but a critical component of achieving it. One of the most compelling metabolic features observed in centenarians is low insulin resistance. In the general aging population, insulin sensitivity tends to decline over time, promoting hyperinsulinemia, abdominal adiposity, and increased systemic inflammation. However, studies of long-lived individuals often show fasting insulin levels and HOMA-IR, homeostatic model assessment for insulin resistance, values well below age-matched peers. This relative metabolic efficiency may reflect both genetic predispositions and lifelong dietary habits that favor glucose homeostasis. Even more interestingly, offspring of centenarians, who are themselves more likely to age successfully, also show superior insulin sensitivity in midlife compared to control populations, suggesting a heritable or early environmental component to metabolic resilience. In tandem with insulin sensitivity, lipid profiles in centenarians tend to be unusually stable and protective. While most older adults experience rising levels of LDL cholesterol, triglycerides, and oxidized lipids, many centenarians maintain favorable ratios of LDL to HDL cholesterol and low circulating levels of atherogenic lipoproteins. Genetic variants related to apolipoprotein E, particularly the ApoE2 allele and CETP, cholesterol ester transfer protein, have been implicated in this profile, contributing to efficient lipid transport and reduced arterial plaque formation. These lipid advantages are not limited to cholesterol levels. They also encompass particle size and composition, with centenarians often showing larger, less dense LDL particles and elevated HDL subtypes that promote reverse cholesterol transport. Antioxidant defense is another area where the metabolic signatures of centenarians diverge markedly from typical aging patterns. Aging is associated with an accumulation of reactive oxygen species, ROS, that damage proteins, lipids, and DNA. In most individuals, antioxidant capacity declines over time, tipping the balance toward oxidative damage. Long-lived individuals, however, often demonstrate sustained activity of key antioxidant enzymes such as superoxide dismutase, SOD, catalase, and glutathione peroxidase. Blood markers of oxidative stress such as malondialdehyde, NDA, and 8-hydroxy-2-deoxyguanosine 8-OHDG tend to be lower in these individuals, suggesting they are not only producing fewer ROS, but are also more effective at neutralizing them. This enhanced redox balance likely plays a protective role across tissues, particularly in the cardiovascular system and the brain. Beyond these classical markers, centenarians also display distinct hormonal and nutrient-sensing profiles. IGF-1, insulin-like growth factor 1, a key hormone in the growth and repair pathways, often appears in lower concentrations in centenarians, reflecting a downregulation of anabolic signaling that has been associated with increased longevity in animal models. This dampened IGF-1 signaling may reduce cancer risk and slow cellular aging by minimizing growth-driven damage. Other markers, such as adiponectin, an anti-inflammatory hormone released by fat cells, tend to be elevated in long-lived individuals and correlate with enhanced insulin sensitivity and reduced inflammation. Additionally, amino acid and metabolic byproduct profiles in centenarians often differ from those in the general elderly population. Lower levels of branched-chain amino acids, BCAAs, and homocysteine, a byproduct of methionine metabolism linked to cardiovascular and cognitive decline, have been observed, reflecting a metabolic state that favors repair and detoxification over excess growth or protein accumulation. Importantly, these beneficial metabolic signatures appear to arise not from aggressive intervention, but from long-standing physiological balance. Many centenarians have never followed specific diets or fitness routines in a modern sense, yet their habitual lifestyles, often rooted in traditional eating patterns, daily physical activity, and consistent social engagement, have helped preserve optimal metabolic function over time. These choices seem to have cumulative effects, buffering the gradual dysregulation typically associated with aging. The metabolic health of the oldest old challenges assumptions about what is biologically inevitable in aging. Rather than a steady decline in glucose regulation, lipid metabolism, and oxidative balance, these individuals exhibit a pattern of maintained equilibrium, suggesting that aging does not have to entail metabolic breakdown. As a result, measuring and understanding these metabolic markers in midlife and earlier may help predict and potentially influence who is likely to experience a longer, healthier life. This metabolic phenotype of longevity also offers a template for intervention. Lifestyle strategies that improve insulin sensitivity, optimize lipid profiles, and enhance antioxidant defenses, such as time-restricted eating, moderate-intensity exercise, plant-forward diets, and stress management, are now being tested not just to prevent disease, but to slow biological aging itself. By learning from those who have aged successfully and decoding the blood chemistry that supports their resilience, we may soon be able to translate their advantages into practical tools for broader populations. Metabolic health, far from being a passive reflection of age, is emerging as a key driver of how well we age.